Look up at the night sky on a clear evening. Beyond the glow of our cities, an expanse of unimaginable scale stretches out in every direction. For millennia, humanity has stared into this cosmic ocean, mapping the brightest stars and wondering what lies in the vast, silent dark between them. We are a species bound by gravity to a small, rocky world. Yet our collective curiosity has always possessed an escape velocity of its own. We have always needed to know what lies over the next horizon. In the late 1970s, that insatiable curiosity took a tangible, metallic form. We didn't just look up, we reached out. We built two robotic emissaries out of aluminum, gold, and silicon, and hurled them into the void. This was the genesis of the Voyager program, an endeavor that stands today as one of the most audacious and scientifically triumphant chapters in human history. Voyager 1 and Voyager 2 had a thrilling primary mission. Their mandate was to conduct a grand tour of the outer planets. But the visionary architects of Voyager harbored a far more expansive dream. They knew that if these twin probes survived the punishing radiation of Jupiter and the hazardous rings of Saturn, their incredible momentum would carry them on a permanent, one-way trajectory. They would inevitably become the first human-made objects to pierce the heliosphere and sail into the uncharted, frigid waters of interstellar space. This is not merely a story about machines gathering data. It is the ultimate narrative of our outward urge. It is the chronicle of how two one-ton probes fundamentally rewrote textbooks, transformed our understanding of planetary science, and crossed the ultimate threshold into the stellar neighborhood. The Voyagers have outlived their creators' wildest expectations, continuing to whisper secrets back to Earth even as their nuclear power slowly dwindles. This is the story of humanity's greatest and longest expedition, our eternal journey to the stars. To fully comprehend the magnitude of the Voyager launches in the late summer of 1977, one must first look backward at the geopolitical and scientific landscape of the decade that preceded them. The story of Voyager does not begin on a launch pad in Florida, but rather in the quiet, chalk dust-filled offices of the Jet Propulsion Laboratory in California during the mid-1960s. The 1960s were defined by the breathless, frenetic sprint to the moon. Driven by the existential pressures of the Cold War, the United States and the Soviet Union poured unprecedented resources into their respective space programs. When Neil Armstrong and Buzz Aldrin set foot on the lunar surface in 1969, the geopolitical objective of the space race was effectively achieved. However, this triumph brought an immediate, sobering hangover for NASA. With the primary goal accomplished, public enthusiasm began to wane, and political priorities shifted back toward terrestrial concerns. The Vietnam War, civil rights movements, and economic instability. NASA's budget, which had peaked at nearly 4.5% of the federal budget during the height of Project Apollo, was rapidly slashed. The agency was forced to transition from an era of seemingly unlimited funding to one of strict austerity. The future of human spaceflight was being funneled into the development of the space shuttle, leaving deep space planetary exploration fighting for its very survival. It was against this backdrop of shrinking budgets that a remarkable mathematical discovery was made. In 1965, a young aerospace engineer at JPL named Gary Flandreau was tasked with studying the orbital mechanics of the outer planets: Jupiter, Saturn, Uranus, and Neptune. Flandreau was specifically looking at a technique called a gravity assist. The concept was theoretically simple, but practically complex. A spacecraft could fly close behind a massive planet, stealing a microscopic fraction of the planet's orbital momentum to slingshot itself forward, dramatically increasing its speed and changing its trajectory without expending any onboard rocket fuel. While plotting the orbits of the outer planets, Flandreau realized something astonishing. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune would arrange themselves in a sweeping, sequential arc. This particular planetary alignment was exceedingly rare, occurring only once every 176 years. If a spacecraft were launched during a specific window in the late 1970s, it could ride this string of cosmic pearls, using Jupiter's immense gravity to slingshot to Saturn, Saturn's gravity to reach Uranus, and Uranus to reach Neptune. This trajectory, which Flandreau dubbed the Grand Tour, would reduce the flight time to Neptune from a staggering 30 years down to a mere 12. It was a once-in-a-century opportunity. The scientific community was electrified. NASA initially proposed an ambitious multi-billion-dollar fleet of heavily armored probes to conduct the Grand Tour. However, the Nixon administration, focused on cutting costs, balked at the price tag. In 1972, the Grand Tour was officially cancelled, replaced by a much cheaper, stripped-down mission called Mariner Jupiter-Saturn 1977. MJS-77 was officially funded only to build 2 probes that would fly past Jupiter and Saturn. A trip to Uranus and Neptune was strictly off the books. But the engineers at Jet Propulsion Laboratory were dreamers as well as pragmatists. They knew the alignment was too precious to waste. While officially building spacecraft that would only last for a 5-year mission to Saturn, they quietly over-engineered every single component, building vessels robust enough to survive the cold, dark, decades-long journey to the ice giants and beyond. Shortly before launch, recognizing that these deeply modified probes were vastly superior to the old Mariner spacecraft, NASA officially renamed the project Voyager. But what did humanity actually know about the outer solar system in the mid-1970s? The truthful answer was very little. Before Voyager, our understanding of Jupiter and Saturn was largely based on blurry, shimmering observations made through Earth-based telescopes. We knew Jupiter was a massive sphere of hydrogen and helium, featuring a great red spot. And we knew Saturn had a system of beautiful, mysterious rings. The Pioneer 10 and Pioneer 11 spacecraft had blazed the trail in 1973 and 1974, proving that a spacecraft could survive traversing the asteroid belt and the lethal radiation fields surrounding Jupiter. However, the Pioneer probes were rudimentary pathfinders, equipped with relatively simple instruments. Voyager, by contrast, was designed to be a state-of-the-art flying observatory. The original official goals of the mission were tightly focused on the Jupiter and Saturn systems, specifically targeting their atmospheres, their magnetic fields, and their complex families of moons. Scientists wanted to understand the weather on worlds where there is no solid surface. What was driving the ferocious 400-mile-per-hour winds of Jupiter? Was the Great Red Spot a permanent feature or a transient storm? by carrying highly advanced Vidicon cameras, essentially early television cameras modified for deep space, and infrared spectrometers. The Voyagers were tasked with analyzing the chemical composition and temperature profiles of these churning alien atmospheres, searching for the primordial materials left over from the formation of the solar system. Saturn's rings had baffled astronomers since Galileo first observed them in 1610. Were they solid disks? Were they made of gas, dust, or ice? How did they maintain their shape? The mission goal was to photograph the rings in high resolution, measure their thickness, and determine their composition by watching starlight pass through them. Perhaps the most crucial scientific objective lay not with the planets themselves, but with their moons. Prior to Voyager, moons were generally assumed to be geologically dead, crater-pocked spheres resembling our own moon. Voyager was tasked with mapping Jupiter's 4 largest moons: Io, Europa, Ganymede, and Callisto. Even more important was Saturn's largest moon, Titan. Earth-based observations had revealed that Titan possessed an atmosphere, making it entirely unique among the moons of the solar system. Some scientists speculated that Titan's atmosphere might be similar to the primordial atmosphere of early Earth, potentially harboring complex organic chemistry. Studying Titan was deemed so vital that Voyager 1's entire trajectory was specifically designed to ensure a close, incredibly precise flyby of this mysterious, smog-shrouded moon, even if it meant sacrificing a continued journey to Uranus and Neptune. To accomplish these goals, the spacecraft had to be a marvel of 1970s engineering. Because solar panels are virtually useless in the dim twilight of the outer solar system, the probes were powered by radioisotope thermoelectric generators. These devices generated electricity by converting the heat released from the natural radioactive decay of a sphere of plutonium-238. Furthermore, because radio signals would take hours to travel between the spacecraft and Earth, the Voyagers could not be flown with a joystick. They required autonomous onboard computers. Each probe was equipped with 3 dual-redundant computer systems, which astonishingly possessed a combined memory of just 68 kilobytes, a fraction of the data contained in a single modern digital photograph. Yet these incredibly robust systems were programmed to manage power, aim instruments, and protect the spacecraft in the harsh void. As the summer of 1977 reached its peak, 2 pristine spacecraft sat atop towering rockets at the Kennedy Space Center in Cape Canaveral, Florida. The launch schedule was tight, governed by the unyielding celestial mechanics of the 176-year alignment. Counterintuitively, Voyager 2 was scheduled to launch first. The reasoning lay in their distinct trajectories. Voyager 2 was assigned the slow and scenic route. Its trajectory was meticulously calculated to fly past Jupiter and Saturn at specific angles that would preserve the option, the unofficial, whispered hope of the JPL engineers to continue on to Uranus and Neptune. Voyager 1, conversely, was taking the fast track. Its trajectory was optimized to reach Jupiter and Saturn much more quickly, prioritizing the critical flyby of Titan. Because Voyager 1 would travel at a higher velocity, it would overtake Voyager 2 in the asteroid belt, arriving at Jupiter 4 months earlier, despite launching later. On the morning of August 20th, 1977, Voyager 2 lifted off atop a massive Titan III E Centaur launch vehicle. The Titan was a brute force rocket originally designed as an intercontinental ballistic missile, paired with a sophisticated, liquid hydrogen-fueled Centaur upper stage that would provide the final kick out of Earth's orbit. As the rocket roared into the Florida sky, the mission nearly ended in disaster before it had even truly begun. The tremendous vibrations and gravitational forces of the launch severely confused Voyager 2's onboard computers. The spacecraft's gyroscopes, which told it which way was up and how it was oriented in space, began registering anomalous data. Believing it was spinning out of control or experiencing a catastrophic failure, Voyager 2's autonomous safety protocols took over. The computer effectively mutinied. It shut down the main high-gain antenna, switched to a faint, low-power backup radio, and began frantically firing its thrusters in a desperate attempt to stabilize itself. Back at JPL Mission Control in Pasadena, the telemetry screens went dark. Engineers watched in horror as they lost their primary connection to the spacecraft just minutes into its decade-long journey. For several agonizing days, the team worked around the clock, sending blind commands through the deep space network to coax the spacecraft out of its paranoid safety mode. Eventually, the engineers realized the spacecraft wasn't broken. It was simply dizzy from the launch. Once they convinced the computer to ignore the initial faulty gyroscope readings, Voyager 2 settled down, deployed its scientific booms, and began its long cruise toward Jupiter. "16 days later, on September 5th, 1977, it was Voyager 1's turn. The atmosphere in mission control was tense, still raw from the near loss of Voyager 2. As the countdown reached zero, the Titan 3E rocket ignited, lifting Voyager 1 into the morning sky. Once again, disaster loomed. This time, not from the spacecraft's software, but from the physical hardware of the rocket itself. During the ascent, the Titan booster developed a minute leak in a propellant line. It was a subtle failure, but in the unforgiving mathematics of rocketry, it was almost fatal. Because of the leak, the Titan rocket underperformed, failing to provide the necessary thrust and velocity before it burned out and detached. When the Centaur upper stage ignited to push Voyager 1 out of Earth orbit, its onboard guidance system instantly recognized the problem. The rocket was flying too low and too slow. To reach Jupiter, the Centaur would have to burn its own fuel for much longer than planned to make up for the Titan's shortfall. Engineers watched the telemetry with bated breath as the Centaur's engines burned continuously, draining its fuel tanks at an alarming rate. It was a race against physics. If the Centaur ran out of fuel before reaching the precise escape velocity required, Voyager 1 would not make it to Jupiter. It would fall into a useless orbit around the Sun. The Centaur engines finally shut down, having successfully pushed Voyager 1 onto the correct trajectory. When engineers checked the data, they were stunned. The Centaur upper stage had compensated for the massive deficit, but the margins were terrifyingly thin. When the engines cut off, the Centaur had only 3.4 seconds of usable propellant left in its tanks. Had the Titan booster underperformed even a fraction of a percent more, Voyager 1, the spacecraft destined to become the first human-made object to enter interstellar space, would have been a complete failure. Instead, it was perfectly on course. Within weeks, both spacecraft had safely crossed the orbit of the Moon. The umbilical cords of launch were severed. The violent roar of the rockets was replaced by the silent, frictionless coasting of deep space. Humanity's two greatest explorers had survived their fiery births and were now outward bound, carrying with them the hopes of an entire species and a golden record containing the murmurs of our world. The Grand Tour had officially begun. After successfully navigating the treacherous expanse of the asteroid belt, the twin Voyager spacecraft left the realm of the terrestrial, rocky planets behind. They were entering a domain of giants, a region of the solar system dominated by colossal spheres of swirling gas, supercompressed fluids, and primordial ice. The ensuing encounters with Jupiter, Saturn, Uranus, and Neptune between 1979 and 1989 would not merely add footnotes to existing astronomical textbooks, they would require those textbooks to be entirely rewritten. The Grand Tour was about to fundamentally shatter humanity's preconceived notions of the cosmos, transforming our understanding from a static, dead solar system into a dynamic, violently active, and endlessly diverse neighborhood. As Voyager 1 approached Jupiter in early 1979, the sheer scale of the planet began to overwhelm the spacecraft's narrow-angle cameras. Jupiter is so massive that it could comfortably contain more than 1,300 Earths. The planet's gravitational pull is immense, acting as a cosmic vacuum cleaner that severely shapes the environment of the inner solar system. But along with immense gravity comes immense danger. Jupiter possesses a magnetosphere so powerful and heavily laced with trapped high-energy radiation that it threatened to fry the Voyager's delicate 1970s-era electronics before they could even beam their data back to Earth. In March 1979, Voyager 1 made its closest approach, followed by Voyager 2 4 months later in July. The images they returned stunned mission control at the Jet Propulsion Laboratory. Earth-based telescopes had previously shown Jupiter as a somewhat static, banded sphere. The Voyagers revealed a churning, violent, hyperactive fluid dynamics laboratory. The cameras captured intricate swirling storm systems, convective cells, and jet streams moving at wildly different speeds. The centerpiece of this meteorological chaos was the Great Red Spot, a colossal anticyclonic storm large enough to swallow Earth whole. The Voyager probes provided the first high-resolution time-lapse movies of this atmospheric behemoth, revealing that it was not a solid feature, but a complex rotating vortex rotating counterclockwise, consuming smaller storms that strayed too close to its periphery. Before Voyager, the scientific consensus held that moons in the outer solar system were dead, frozen, heavily cratered relics of the early solar system, much like our own moon. They were expected to be geologically silent. Voyager 1 obliterated this assumption in a single afternoon. While analyzing navigation images of Jupiter's moon, Io, JPL navigation engineer Linda Morabito noticed a bizarre, umbrella-shaped anomaly rising from the moon's edge. It was not a glitch, it was a volcanic plume erupting hundreds of miles into the vacuum of space. Io, caught in a brutal gravitational tug-of-war between Jupiter's immense mass and the gravity of the other large moons, is subjected to intense tidal heating. The solid rock of the moon is stretched and squeezed by up to 100 meters per orbit, generating massive internal friction that melts rock and fuels the most violently active volcanism in the solar system. The discovery of active volcanoes on Io was arguably the single most important discovery of the planetary encounters, proving that geological activity could exist far beyond the heat of the Sun. The surprises continued with the moon Europa. Voyager revealed a surface devoid of mountains or significant craters, covered instead in a smooth crust of water ice, heavily fractured by dark, intersecting lines. This incredibly smooth, cracked topography strongly suggested that Europa's icy shell was floating atop a vast, hidden ocean of liquid water, kept warm by the same tidal forces torturing Io. Almost as an afterthought, as Voyager 1 looked back at Jupiter from the planet's dark side, it captured images of a faint, dusty ring system. Jupiter, it turned out, also possessed rings, though they were made of microscopic dust particles blasted off its innermost moons by micrometeorite impacts, rather than the brilliant ice of Saturn's rings. Catapulted by Jupiter's massive gravity, both spacecraft hurtled toward the crown jewel of the solar system, Saturn. Voyager 1 arrived in November 1980, with Voyager 2 following in August 1981. If Jupiter was a study in violent fluid dynamics, Saturn was a masterclass in elegant, baffling orbital mechanics. For centuries, astronomers believed Saturn's rings were composed of a few broad, flat, uniform sheets of material separated by wide gaps. As the Voyager probes approached, their cameras revealed a staggering level of complexity. The rings were not solid bands. They were composed of thousands upon thousands of individual, distinct ringlets, resembling the microscopic grooves on a phonograph record. Even more astonishing were the gravitational dynamics governing this system. The Voyagers discovered tiny shepherd moons embedded within the rings. The gravity of these tiny, icy worlds acts like a celestial sheepdog, clearing gaps in the rings and herding the icy particles into sharply defined boundaries. In the narrow outer F-ring, Voyager captured images of twisted, braided structures, a complex gravitational dance caused by two shepherd moons, Prometheus and Pandora, orbiting on either side of the ring. Saturn possesses an extensive family of moons, including Enceladus, which Voyager revealed to be incredibly bright and covered in strange, smooth terrains, hinting at recent geological activity. There was also Iapetus, a bizarre world with one hemisphere as bright as snow and the other as dark as charcoal. But the primary target of the entire Voyager 1 mission was Saturn's largest moon, Titan. Earth-based observations had confirmed that Titan was the only moon in the solar system with a substantial atmosphere. In fact, its atmosphere was thicker than Earth's, completely obscuring the surface beneath a dense, orange photochemical smog. Scientists theorized that Titan's nitrogen and methane-rich atmosphere might resemble the primordial conditions of an early Earth before the emergence of life. NASA leadership deemed the exploration of Titan so critical that Voyager 1's flight path was specifically designed to fly within 4,000 miles of the Moon. This close approach allowed Voyager 1's instruments to peer into the atmosphere, confirming it was rich in complex organic molecules and hinting that it might rain liquid methane onto the hidden surface. However, this encounter came at a steep operational cost. To execute the Titan flyby, Voyager 1 had to use Saturn's gravity to swing itself sharply upward, permanently vaulting out of the ecliptic plane, the flat disk where most planets orbit. The grand tour was over for Voyager 1. Its planetary exploration was complete. From that moment in late 1980, it began its long, lonely climb, upward and outward, toward interstellar space. The burden of completing the grand tour now fell entirely on the shoulders of Voyager 2. Using Saturn's gravity, Voyager 2 was precisely aimed on a 5-year cruise toward a planet no spacecraft had ever visited. In January 1986, nearly 9 years after leaving Earth, Voyager 2 arrived at Uranus. The spacecraft was operating in a radically different environment. Sunlight at Uranus is roughly 400 times weaker than it is at Earth. To capture images in this deep twilight without blurring them, the spacecraft's cameras required very long exposure times. However, because Voyager 2 was hurtling past the planet at nearly 40,000 miles per hour, the cameras had to physically pan to track their targets, a complex maneuver that the aging 1970s spacecraft was never originally designed to perform. In a triumph of long-distance engineering, NASA completely reprogrammed Voyager 2's onboard computers during the 5-year cruise from Saturn. They upgraded the image processing software, implemented new data compression techniques to squeeze more information through the fading radio signal, and taught the spacecraft how to steadily rotate itself to keep the cameras locked on target. Visually, Uranus appeared as a featureless, pale blue-green sphere, colored by the methane in its upper atmosphere. But beneath this bland exterior, Voyager 2 discovered a deeply bizarre world. Unlike every other planet in the solar system, which spins somewhat upright like a top, Uranus is knocked onto its side, rotating at a 98-degree angle with its poles pointing directly toward the Sun. Voyager 2 confirmed that this severe tilt causes extreme, decades-long seasons. More baffling was the planet's magnetic field. Earth and Jupiter have magnetic fields roughly aligned with their rotational poles. Voyager 2 discovered that Uranus's magnetic field is tilted 60 degrees away from its axis of rotation and, remarkably, does not even originate from the center of the planet. It is wildly off-center, suggesting the field is generated by an electrically conductive, superpressurized ocean of water and ammonia deep within the icy mantle, rather than a molten core. Voyager 2 also discovered 10 new moons and a system of incredibly dark, narrow rings. The most spectacular imagery, however, came from a small moon named Miranda. Miranda looked as though it had been blown apart in a catastrophic collision and hastily reassembled in the dark. With a diameter of about 500 kilometers, it is composed mostly of ice mixed with rock. Despite its small size, Miranda has one of the most bizarre landscapes in the solar system. Its surface features giant fault canyons, some up to 20 kilometers deep, far deeper than Earth's Grand Canyon. It also hosts unique coronae, patchwork regions of ridges and valleys that look stitched together. Verona Rupes, a towering cliff on Miranda, is the tallest known in the solar system, plunging nearly 20 kilometers. The extreme topography of Miranda proved that even the smallest, coldest bodies at the edge of the solar system possess violent, dramatic geological histories. "12 years and nearly 3 billion miles after leaving Cape Canaveral, Voyager 2 arrived at Neptune in August 1989. This was the final planetary encounter of the Voyager program, and it would be the spacecraft's ultimate masterpiece. Because Neptune is so incredibly far from the Sun, receiving only a fraction of a percent of the solar energy that Earth does, scientists expected it to be a cold, dormant, frozen world. Instead, Voyager 2 revealed a brilliant, azure blue planet exhibiting the most violent weather in the entire solar system. Despite the profound lack of solar heat to drive atmospheric convection, Neptune's atmosphere was chaotic and incredibly active. The spacecraft captured high-altitude clouds composed of frozen methane crystals, casting distinct shadows onto the opaque blue cloud deck below. Dominating the southern hemisphere was the Great Dark Spot, an anticyclonic storm system the size of Earth, highly reminiscent of Jupiter's Great Red Spot. The most shocking revelation, however, was the wind speed. Voyager 2 clocked winds in Neptune's atmosphere, whipping in the opposite direction of the planet's rotation at speeds up to 1,200 miles per hour. Supersonic speeds that defied the thermodynamic models of the era. The internal heat source driving this ferocious meteorology remains a mystery to this day. Just as Titan was the ultimate prize at Saturn, the large moon Triton was the crown jewel of the Neptune encounter. Triton is unique. It orbits Neptune backwards in a retrograde direction, strongly implying it did not form alongside the planet, but is instead a large, icy dwarf planet from the Kuiper Belt that was captured by Neptune's gravity millions of years ago. Voyager 2 flew a mere 2,500 miles above Triton's surface, returning breathtaking images of a terrain that looked like the rind of a cantaloupe. The moon was so cold, plunging to -391 degrees Fahrenheit, that its surface was heavily coated in frozen nitrogen, methane, and carbon monoxide. Yet, incredibly, Triton was alive. Voyager 2 captured dark streaks of soot, being blown across the bright icy surface by a tenuous, microscopic wind. More astonishingly, it photographed active cryovolcanoes, geysers shooting columns of dark, dusty nitrogen gas up to 5 miles high into the thin atmosphere before being sheared off by high-altitude winds. This discovery of cryovolcanism on a frozen world billions of miles from the Sun was a fitting, explosive finale to the Grand Tour. It echoed the volcanic plumes of Io discovered a decade earlier, perfectly bookending a mission defined by the shattering of expectations. When Voyager 2 finally sailed past Neptune and joined its twin on the long trek toward interstellar space, the discipline of planetary science had been irreversibly transformed. Before 1979, the solar system was largely viewed through a terrestrial lens. Earth, Mars, and Venus were the dynamic worlds of interest. Everything beyond the asteroid belt was considered a frozen museum of the early solar system. The Voyagers dismantled that paradigm completely. The incredible diversity of the outer solar system forced scientists to develop a new framework called comparative planetology. By studying the supersonic winds of Neptune, the volcanic chaos of Io, the intricate ring dynamics of Saturn, and the magnetic weirdness of Uranus, scientists could better understand the universal laws of physics, fluid dynamics, and geology as they apply to our own planet. Earth was no longer isolated. It was part of a continuum of planetary evolution. The Grand Tour did not just map new territories, it birthed an entirely new way of looking at the cosmos, proving that the universe is endlessly creative, fiercely dynamic, and deeply, beautifully complex. Bolted to the exterior of both Voyager 1 and Voyager 2, shielded from the micrometeorites and extreme radiation of deep space by a protective aluminum jacket, sits a 12-inch gold-plated copper disc. On its face, it bears the simple, engraved inscription: "To the makers of music, all worlds, all times." This is the Voyager Golden Record. If the spacecraft themselves are a triumph of human engineering, the Golden Record is a triumph of human poetry, art, and philosophical introspection. It is a time capsule, a cosmic greeting card, and a deeply emotional summary of the planet Earth, cast into an ocean of space so vast that its shores are unimaginable. When NASA approved the Voyager mission, the agency recognized the profound symbolic weight of sending objects out of the solar system. The Pioneer 10 and 11 spacecraft, launched a few years earlier, carried a small anodized aluminum plaque bearing a simple line drawing of a man and a woman, along with a map of our solar system. For Voyager, a mission of much greater ambition, NASA wanted a more comprehensive message. They turned to Carl Sagan, an astronomer, astrophysicist, and masterful science communicator at Cornell University. Sagan assembled a small, eclectic committee. This group included astronomer Frank Drake, creator of the Drake equation, author Anne Druyan, science writer Timothy Ferris, artist John Lomberg, and artist Linda Salzman Sagan. They were given an impossibly daunting task: distill the entirety of human existence, the incredible biodiversity of Earth, and the emotional resonance of our species into a single physical medium, and do it in roughly 6 months. The philosophy behind the project was deeply rooted in optimism. Sagan and his team knew the sheer mathematics of interstellar space. The probability of an alien civilization ever stumbling across a silent, unpowered spacecraft in the dark void between stars is infinitesimally small. The Voyagers are not heading toward any specific star, they are simply drifting. However, Sagan argued that the act of creating the message was just as important as its eventual discovery. The spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. The committee faced a critical technological decision. What medium should they use? Magnetic tape, common in the 1970s, would degrade quickly over centuries, erased by ambient cosmic radiation. They ultimately chose a phonograph record, a physical analog disc stamped in copper and plated in gold, could survive the harsh environment of interstellar space for 1 billion years or more without deteriorating. It was a rugged, tangible medium that required relatively simple physics to decode. To ensure that any extraterrestrial intelligence who found the record could actually play it, the protective aluminum jacket of the Golden Record serves as a visual instruction manual. Etched onto the cover are several precise, scientifically universal diagrams. In the top left corner, a drawing of the phonograph and stylus shows the basic playback setup. Around it, arithmetic in binary code, measured by the fundamental transition time of the hydrogen atom, dictates the correct rotational speed of 33 1/3 revolutions per minute. Below this, a diagram illustrates how to reconstruct the record's analog video signals line by line to form a picture, much like an analog television set. Perhaps the most famous engraving on the cover is the pulsar map, originally designed by Frank Drake. It consists of a starburst pattern of 14 lines radiating from a central point representing our Sun. Because pulsars act like cosmic lighthouses with highly specific frequencies, an alien civilization could theoretically triangulate our solar system's location in the Milky Way and calculate the exact epoch of the launch. Finally, a small patch is electroplated with ultra-pure uranium-238. Because it decays into lead at a known constant rate, any civilization Finding the probe billions of years from now could determine exactly how old the record is. The record contains 115 images, encoded not as digital files, but as analog audio signals. Selected by a team led by John Lomberg, the goal was to provide a visual encyclopedia of Earth. The sequence establishes a scientific baseline with mathematical definitions, human anatomy, and the double helix structure of DNA. It then blossoms into the natural world, featuring diverse landscapes, breaching dolphins, and soaring eagles. Humanity is depicted through our diversity, ingenuity, and daily life. There are photographs of a woman in a supermarket, Olympic sprinters, a Balinese dancer, the Taj Mahal, and a Saturn V rocket lifting off. Crucially, the committee deliberately excluded images of war, poverty, disease, and nuclear explosions. Carl Sagan's team vetoed overtly political imagery to present an aspirational portrait of a vibrant planet, choosing to send our hopes and determination rather than our worst mistakes. If the images provide visual context, the audio tracks provide Earth's soul. The record features greetings in 55 languages, reflecting our vast linguistic heritage. The messages themselves are brief but poignant. Some are formal, like the Arabic greeting. Others are deeply intimate, such as the Amoy Minnan message. The English greeting was provided by the young son of Carl Sagan's friend, who simply says, "Hello, from the children of planet Earth." Following the greetings is a 12-minute audio montage titled The Sounds of Earth, conceived and produced by Anne Druyan. It is a sonic history of our planet's evolution. It progresses from geological phenomena like grinding tectonic plates to biological life, featuring humpback whales and chimpanzees. It concludes with human sounds, a tractor, a rocket launch, a mother's kiss, and a heartbeat. Hidden within this section is a uniquely profound artifact. Anne Druyan underwent an electroencephalogram while she meditated on various topics, ranging from the history of civilization to the violence of the world, and finally, to what it felt like to be newly in love. Her brainwaves, heart rate, and eye movements were compressed into a 1-minute audio file, literally embedding the neurological signature of human love into the grooves of the record. The bulk of the record, nearly 90 minutes, is dedicated to music, viewed by the committee as a universal language blending mathematical precision with raw emotional power. Ethnomusicologist Alan Lomax helped curate an eclectic anthology to avoid a purely Western-centric playlist. Western classical is represented by the mathematical brilliance of Bach, Beethoven's Symphony No. 5, Mozart, and Stravinsky. The inclusion of contemporary music sparked intense debate. Sagan successfully fought to include Chuck Berry's Johnny B. Good over objections that rock was adolescent, noting that Earth has many adolescents. Perhaps the most emotionally devastating piece is Blind Willie Johnson's 1927 track. Featuring mournful humming and slide guitar, it conveys profound isolation and mortality. It was included because painting a portrait of Earth without acknowledging our capacity for sorrow would have been dishonest, standing as a beautiful expression of human vulnerability drifting through space. The Voyager Golden Record is ultimately an exercise in profound, almost agonizing optimism. It is a monument to a brief moment in time when a single species on a small blue planet managed to quiet its internal conflicts long enough to look outward and say, in a unified voice, "We are here." The symbolism of this time capsule extends far beyond the possibility of alien contact. The true audience for the Golden Record is not the extraterrestrials who might intercept it millions of years from now. The true audience is us. It is a mirror held up to humanity. In the process of deciding what to send to the stars, we were forced to evaluate who we are, what we value, and what we wish to be remembered for. Long after the pyramids have eroded into dust, long after the oceans have boiled away, and the Earth has been swallowed by the expanding red giant of our dying sun, the Voyager probes will still be traveling. The gold-plated copper discs will remain intact. Following Voyager 2's spectacular flyby of Neptune in August 1989, the primary phase of the Grand Tour was officially complete. The planets of the outer solar system were now entirely behind the twin spacecraft. In 1990, Carl Sagan convinced NASA to turn Voyager 1's cameras back toward the inner solar system one last time, to capture the iconic pale blue dot photograph. Voyager 1 executed a command that had no scientific value whatsoever. From a distance of 3.7 billion miles, far beyond the orbit of Neptune, the spacecraft turned its cameras backward and took a mosaic of 60 individual frames, capturing Venus, Earth, Jupiter, Saturn, Uranus, and Neptune. In the frame containing Earth, our entire planet appears as a fraction of a single pixel. A microscopic, pale blue speck suspended in a scattered ray of sunlight against the immense, crushing blackness of deep space. Sagan later immortalized this image in his book, Pale Blue Dot, A Vision of the Human Future in Space. His reflection on the photograph remains one of the most poignant pieces of literature ever written about the human condition. That single image did more to contextualize the fragility of our planet and the artificial nature of human borders than any piece of art or political discourse in modern history. It became a rallying cry for environmentalism and a sobering reminder of our shared destiny. Shortly after that shutter clicked, mission controllers sent the commands to permanently power down the imaging systems on both probes. With no more planets to photograph, keeping the cameras warm and operational was an unnecessary drain on the spacecraft's slowly depleting nuclear power sources. The Voyagers were now flying blind, but they were not dead. They were transitioning into a completely new, arguably more profound, phase of their existence: the Voyager Interstellar mission. Their new, singular objective was to find the edge of our solar system, cross it, and become the first human-made objects to sail into the cosmic ocean of interstellar space. To understand what it means to leave the solar system, one must first discard the notion that the solar system ends at the orbit of the furthest planet. The true boundary of our local neighborhood is dictated not by gravity, but by the overwhelming magnetic and energetic influence of our sun. The sun is not a quiet, static sphere of light. It is a raging thermonuclear furnace that constantly exhales a million-mile-per-hour gale of electrified particles, mostly protons and electrons. This continuous outward blast is known as the solar wind. As the solar wind races outward in all directions, it inflates a gargantuan magnetic bubble that encompasses all the planets, the asteroid belt, and the Kuiper belt. This protective bubble is called the heliosphere. For decades, astrophysicists theorized about the anatomy of this bubble, But until the Voyagers reached its outer limits, it was purely hypothetical. The architecture of the heliosphere, as revealed by the probes, consists of several distinct turbulent zones. As the solar wind travels billions of miles away from the Sun, it eventually begins to push against the interstellar medium, the gas, dust, and radiation that fills the space between the stars. The point at which the million-mile-per-hour solar wind abruptly slows down below supersonic speeds and compresses is called the termination shock. It is much like the sudden, turbulent ring of water that forms at the bottom of a sink when water flows out of a faucet and hits the basin. Voyager 1 crossed this violent boundary in December 2004 at a distance of 94 astronomical units, 94 times the distance between the Earth and the Sun. Voyager 2 crossed it in 2007. Beyond the termination shock lies the heliosheath. This is the outer rind of the solar bubble. Here, the solar wind is dense, hot, and sluggish, swirling and compressing as it reacts to the immense pressure of the interstellar space, pushing back against it. The Voyagers spent years traversing this chaotic, frothing region, functioning as deep space weather stations. But heliosheath is not the end. Beyond it lies the ultimate frontier, the heliopause. It is the precise, theoretical boundary where the outward pressure of the solar wind is finally completely matched and overcome by the inward pressure of the interstellar medium. It is the absolute edge of the Sun's atmospheric dominance. Cross this line and you have officially left the solar system. The term interstellar space conjures images of absolute, pristine emptiness. However, the void between the stars is not truly empty. It is a dynamic, complex environment filled with the interstellar medium. The interstellar medium is primarily composed of hydrogen and helium gas, mixed with incredibly fine grains of carbon and silicate dust. These are the ancient, scattered ashes of dead stars and the primordial building blocks of new ones. While it is a vacuum, far more perfect than anything we can create on Earth, containing roughly 1 atom per cubic centimeter compared to the quintillions of atoms in a cubic centimeter of air at sea level. Over the vast distances of the galaxy, this material adds up to an immense mass and exerts tremendous pressure. Furthermore, interstellar space is practically vibrating with energy. It is bombarded by galactic cosmic rays, high-energy atomic nuclei accelerated to near the speed of light by catastrophic cosmic events, such as the explosive deaths of massive stars millions of years ago. Entering interstellar space means stepping out of the protective shelter of the heliosphere and directly into this ancient, highly radioactive galactic storm. As Voyager 1 pressed deeper into the heliosheath in the late 2000s and early 2010s, the scientific community waited with bated breath. Nobody knew exactly how thick the heliosheath was, or what the crossing of the heliopause would look like in the data. Because the cameras were off, the mission relied entirely on instruments measuring invisible phenomena. The cosmic ray subsystem, the low-energy charged particle instrument, the magnetometer, and the plasma wave subsystem. In mid-2012, the data coming back from Voyager 1, now more than 11 billion miles from Earth, became incredibly strange and contradictory. The spacecraft entered a region scientists dubbed the magnetic highway. The data showed that high-energy galactic cosmic rays from outside the solar system were pouring in at unprecedented levels, suggesting the spacecraft was outside the bubble. However, the magnetic field lines were still perfectly aligned with the Sun's magnetic field, and the amount of low-energy solar particles generated by the Sun remained stubbornly high. It was a bizarre purgatory. The spacecraft seemed to be inside and outside the solar system simultaneously. The scientific team, led by Dr. Ed Stone, the mission's project scientist since 1972, agonized over the interpretation. Had Voyager 1 crossed the edge, or was it just in a new, weird layer of the helio sheath? The definitive answer came from a sudden dramatic shift in the invisible particle counts. On August 25, 2012, Voyager 1 recorded a sheer, precipitous cliff in the data. The levels of low-energy particles originating from the Sun, the very breath of our star, plummeted to near zero. Simultaneously, the intensity of high-energy galactic cosmic rays from the depths of space skyrocketed to record highs and leveled off. It was a staggering transition, but because the magnetic field direction hadn't shifted as theorists predicted it would, the scientific team remained cautious, holding off on an official announcement. They needed one more piece of the puzzle: a direct measurement of the plasma density. Scientists knew that the plasma in interstellar space should be significantly colder and denser than the hot, diffuse plasma inside the solar bubble. Unfortunately, Voyager 1's dedicated plasma science instrument had failed in 1980. The team had to wait for a stroke of cosmic luck. That luck arrived in the form of a massive solar flare. In March 2012, the Sun hurled a massive coronal mass ejection outward. It took 13 months for that shockwave of solar energy to travel the 11 billion miles to Voyager 1. When the shockwave hit the plasma surrounding the spacecraft in April 2013, it caused the plasma to ring like a bell. Voyager 1's plasma wave subsystem recorded this ringing as an audio frequency. By measuring the pitch of that frequency, scientists could finally calculate the density of the plasma surrounding the spacecraft. The results were undeniable. The pitch indicated a plasma density 40 times greater than what was found in the outer layer of the heliosphere. Voyager 1 was literally swimming in the dense waters of the interstellar medium. The conclusion was inescapable. Voyager 1 had crossed the heliopause on August 25, 2012. It had left the solar system. It was a milestone of human achievement, comparable to the first time early hominids walked out of Africa or the moment the Apollo 11 lunar module touched down on the Moon. We had finally touched the void. While Voyager 1 took the fast track out of the solar system, Voyager 2 was following a different trajectory, heading south below the orbital plane of the planets. Because the heliosphere is shaped by the interstellar wind as the entire solar system orbits the center of the Milky Way, it is not a perfect sphere. It behaves more like a blunt bullet or a comet, with a rounded nose and a trailing tail. Voyager 2 reached the boundary on November 5, 2018, crossing the heliopause at a distance of roughly 119 astronomical units from the Sun. Crucially, Voyager 2's plasma science instrument was still fully operational. This allowed scientists to get direct, real-time measurements of the plasma temperature, density, and velocity as the spacecraft pierced the boundary. Unlike Voyager 1's prolonged and confusing transition through the magnetic highway, Voyager 2 experienced a remarkably sharp and sudden crossing, completely transitioning from the solar domain to the interstellar medium in less than a day. The data from Voyager 2 confirmed that the heliopause is not a fuzzy, gradual transition zone, but a distinct, physical boundary wall holding back the galactic tide. The data collected by the twin probes at and beyond the heliopause completely revolutionized our understanding of our place in the galaxy, providing the first direct measurements of a pristine environment we had previously only guessed at. Perhaps the most crucial existential discovery made at the boundary was quantifying exactly how much protection the heliosphere provides. The data revealed that the heliosphere acts as a magnificent, invisible shield for the solar system. By measuring the intensity of the galactic cosmic rays inside the bubble versus outside, scientists calculated that the heliosphere blocks roughly 70% to 75% of the deadly, high-energy cosmic radiation zipping through the interstellar medium. Without this magnetic bubble pushing back against the galaxy, the Earth would be constantly bombarded by a lethal rain of radiation, fundamentally altering the chemistry of our atmosphere, and likely making the evolution of complex life far more difficult, if not impossible. The Voyagers proved that our sun does not just warm us, it actively protects us from the hostile, wider universe. As the Voyagers have pushed further into interstellar space, Voyager 1 is now over 15.9 billion miles away. They continue to send back perplexing data. Counterintuitively, the further they travel from the heliopause, the denser the interstellar plasma seems to become. Scientists theorize this might be due to the interstellar magnetic field lines compressing as they drape over the heliosphere, but the exact mechanics remain one of the many mysteries the probes are currently exploring. Today, the Voyagers operate as humanity's most distant outposts. They are tasting the ancient stardust of the Milky Way and feeling the magnetic heartbeat of the galaxy. By crossing the heliopause, they transformed humanity into an interstellar species, proving that our reach can far exceed the gravitational grasp of our home star. The boundary has been crossed, and the true, eternal journey through the darkness has just begun. The fact that humanity is still receiving science data from spacecraft launched during the Carter administration is nothing short of an engineering miracle. The Voyagers were built in an era before the advent of the modern microprocessor, utilizing computers with thousands of times less memory than a modern smart light bulb. Yet, more than 45 years later, they continue to phone home from the abyss. The secret to the Voyager's longevity lies in their power source. Because solar panels are utterly useless in the pitch-black environment billions of miles from the sun, the spacecraft rely on radioisotope thermoelectric generators. These devices do not use nuclear fission, like a power plant. Rather, they generate electricity by capturing the natural heat released from the radioactive decay of plutonium-238 spheres. However, plutonium-238 has a half-life of 87.7 years. This means the radioactive material is slowly but constantly depleting. Every year, the heat output diminishes, and the Voyagers lose approximately 4 watts of electrical power. To keep the spacecraft alive, the engineering team at NASA's Jet Propulsion Laboratory has had to engage in a decades-long, agonizing process of deep space triage. Slowly, methodically, they have been turning off non-essential systems to conserve power. First went the cameras, then the planetary radio science instruments, then the ultraviolet spectrometers. More recently, the team has had to turn off the internal heaters that keep the remaining instruments from freezing in the absolute cold of deep space. Astonishingly, instruments that were never designed to operate below -30 degrees Fahrenheit have continued to function flawlessly at temperatures plunging below -100 degrees. Powering the instruments is only half the battle. Transmitting that data back to Earth is a monumental challenge in physics. Voyager 1 is currently over 15.9 billion miles away. At that distance, a radio signal traveling at the speed of light, 186,000 miles per second, takes more than 22 hours to reach Earth. A simple hello and a response takes nearly 2 full days. By the time Voyager's radio signal crosses that incomprehensible distance, it is astonishingly faint. The signal striking Earth's surface is roughly 20 billion times weaker than the power required to run an ordinary digital wristwatch. To catch this microscopic whisper, NASA relies on the Deep Space Network, a global array of massive 70-meter-wide radio antennas located in California, Spain, and Australia. These colossal dishes, synchronized to track the spacecraft as the Earth rotates, must be cooled to near absolute zero to eliminate background thermal noise, allowing them to isolate and decode the faint, binary heartbeat of the Voyagers against the roaring static of the cosmos. The survival of the Voyagers is a testament not just to the hardware, but to the brilliant, improvisational minds of the engineers on Earth. Over the decades, the team has had to literally hack the spacecraft to keep them flying. In 2017, scientists noticed that Voyager 1's primary attitude control thrusters, the tiny rockets used to keep the spacecraft's antenna pointed perfectly at Earth, were degrading. If the antenna drifted even a fraction of a degree, the signal would be lost forever. The engineering team dug through decades-old blueprints and decided to fire up a set of backup trajectory correction thrusters that had not been used since the Saturn flyby in 1980. After 37 years of sitting dormant in the freezing vacuum of space, the backup thrusters ignited perfectly, successfully reorienting the spacecraft and extending its life by several years. It was a masterclass in long-distance crisis management. The active phase of the Voyager mission is living on borrowed time. Sometime in the late 2020s, or perhaps the early 2030s, the decaying plutonium-238 inside the radioisotope thermoelectric generators will finally fail to produce the minimum wattage required to power even a single scientific instrument or the radio transmitter. When that inevitable day arrives, the engineers at the Jet Propulsion Laboratory will send their final commands. The spacecraft will return their last packets of telemetry, a faint binary whisper picked up by the massive dishes of the Deep Space Network. And then, the Voyagers will fall utterly, permanently silent. But this silence does not mark the end of the Voyager program. In many ways, it marks the beginning of its most profound phase. Unburdened by the need to communicate with their creators, free from the turbulent solar wind, and perfectly preserved in the vacuum of the interstellar medium, the twin spacecraft will transition from active scientific probes into eternal cosmic monuments. Their mission of exploration will end, but their journey as humanity's definitive time capsules will stretch out across billions of years. To understand the ultimate physical fate of the Voyagers, one must abandon the human concept of time and embrace the dizzying scale of celestial mechanics. Once the power fails, the spacecraft will become dead metal. However, Isaac Newton's first law of motion dictates that an object in motion will stay in motion unless acted upon by an outside force. In the near-perfect vacuum of interstellar space, there is virtually no friction to slow them down. They will continue to coast outward at staggering velocities. Voyager 1 at roughly 38,000 miles per hour, and Voyager 2 at about 35,000 miles per hour. Yet, even at these hypersonic speeds, the distances between the stars are so unimaginably vast that their progress will seem agonizingly slow. It takes a spacecraft traveling at Voyager's speed nearly 18,000 years just to traverse a single light year. Their paths through the Milky Way galaxy have been meticulously calculated. They are not heading toward the center of the galaxy, nor are they trying to escape it. Instead, they are flying outward through the spiral arms, destined to eventually enter a massive, lazy orbit around the galactic core. Voyager 1 is currently heading generally in the direction of the constellation Ophiuchus. For the next tens of thousands of years, it will coast through the local interstellar cloud, encountering nothing but scattered atoms of hydrogen and microscopic dust grains. In approximately 40,000 years, it will experience its first notable celestial encounter, passing within 1.6 light-years of an obscure dim red dwarf star known as Gliese 445. Interestingly, Gliese 445 is actually moving toward our solar system much faster than Voyager 1 is moving toward it. By the time they pass each other in the deep cosmic night, Voyager 1 will be utterly frozen, its golden record waiting silently in the dark. After passing Gliese 445, Voyager 1 will drift endlessly, eventually joining the grand rotation of the Milky Way, completing a single orbit every 225 million years. Voyager 2 is flying on a different vector, heading south relative to the planetary plane, toward the constellations of Sagittarius and Pavo. Like its twin, it faces a journey of profound isolation. In about 40,000 years, Voyager 2 will pass within 1.7 light-years of a small red dwarf called Ross 248. Its most famous encounter, however, will happen in the exceedingly distant future. In roughly 296,000 years, Voyager 2 will pass within 4.3 light-years of Sirius, the brilliant dog star that is currently the brightest star in Earth's night sky. For hundreds of thousands of years, Sirius will grow brighter and brighter from the perspective of the dead probe, eventually blazing like a beacon as Voyager 2 silently glides past, before slowly fading into the backdrop of the galaxy. Barring a direct, catastrophic collision with a rogue asteroid or a star, an event whose probability is so infinitesimally small it is effectively zero, the Voyagers are practically indestructible. They will likely outlive the Earth itself. Given that the Voyagers are carrying the golden record, a literal greeting card meant for extraterrestrial intelligence, the natural question arises: will anyone ever find them? The brutal mathematical reality of the cosmos suggests that the odds of a random alien discovery are vanishingly small. Space is not just vast, it is comprehensively, overwhelmingly empty. Stars are like solitary grains of sand separated by thousands of miles of nothingness. The Voyagers are incredibly tiny objects drifting through a limitless ocean of dark matter and empty space. They emit no light, they will emit no heat, and they will broadcast no radio signals. They will be two cold, dark rocks tumbling through an infinite night. For an alien civilization to stumble upon one of the Voyagers by pure chance is practically impossible. If the golden record is ever retrieved, it will require an extraterrestrial civilization possessing technology far beyond our current comprehension. They would need the ability to scan interstellar space for microscopic metallic anomalies, or they would have to be a sprawling, spacefaring empire that happens to have a localized presence in the exact solar system the Voyager drifts through hundreds of thousands of years from now. But imagine for a moment that against all cosmic odds, the unimaginable happens. Millions of years in the future, an advanced civilization detects a strange, artificial object drifting on the outskirts of their star system. They intercept the battered, micrometeorite-pitted aluminum shell. What happens next? They would find the golden record. As an advanced, spacefaring species, they would immediately recognize the mathematical and physical constants etched onto the cover. They would decode the binary arithmetic based on the fundamental transition of the hydrogen atom. They would recognize the pulsar map and use it to triangulate the origin of the probe, realizing it came from a yellow dwarf star on the other side of the Orion Cygnus arm. By analyzing the ultra-pure uranium-238 electroplated onto the cover, they would calculate its exact age, realizing this relic has been drifting for eons. When they finally place the stylus into the grooves, what will they make of us? Will they have visual receptors capable of interpreting the analog video signals, allowing them to see the face of a human child, the soaring architecture of the Taj Mahal, or the crashing waves of our oceans? Even if their biology is so radically different that they cannot physically hear the music or see the images in the way we do, they will undoubtedly understand the intent. They will analyze the frequencies, decode the data, and realize that this artifact was born of a species with a profound capacity for art, curiosity, and hope. The golden record will tell them that once, on a small blue planet, there lived a civilization that looked up at the stars, felt the crushing weight of their own isolation, and decided to cast a bottle into the cosmic ocean anyway. The ultimate philosophical weight of the Voyager mission lies not in what it found in the outer solar system, but in what it means for the permanence of our species. On Earth, nothing is permanent. Our planet is a highly active, constantly churning geological engine. Plate tectonics slowly erase the surface, pulling ancient continents down into the mantle and forging new ones. Erosion from wind and water grinds mountains down to dust. Even human history is remarkably fragile. Our greatest empires rise and fall in the blink of a geological eye. Our digital records decay, and our physical monuments crumble. Furthermore, the Earth itself has an expiration date. In roughly 5 billion years, our Sun will exhaust the hydrogen fuel in its core. It will begin to burn helium, swelling into a massive red giant. As the Sun's atmosphere expands, it will completely consume the orbits of Mercury and Venus. Earth's oceans will boil away, the atmosphere will be stripped entirely, and the surface will be reduced to an ocean of molten slag if the planet isn't swallowed by the Sun completely. Every book ever written, every song ever sung, every war ever fought, every person who ever lived, all physical evidence that the human race ever existed on this planet will be completely and utterly vaporized. But out in the frigid, preserving depths of interstellar space, the Voyagers will endure. The gold-plated copper records will remain intact, practically immune to the ravages of time. Billions of years from now, long after the Earth is a scorched cinder, Voyager 1 and Voyager 2 will still be orbiting the Milky Way. They will be the absolute final artifacts of human civilization. They are our ultimate monuments. The Voyager mission is the story of humanity at its absolute best. We are a flawed species, prone to violence, division, and short-sightedness. Yet, in the late 1970s, we managed to transcend our terrestrial squabbles. We gathered the finest scientific minds, the most exquisite art, the most diverse languages, and the sheer, brazen audacity to build a machine capable of outliving its creators by billions of years. The eternal journey of the Voyagers ensures that we will not be completely forgotten by the universe. They guarantee that our legacy is not just the ash of a dying star, but a beautifully curated record of a vibrant, curious, and deeply feeling species that managed for a brief, shining moment to touch the eternal darkness and leave a mark. The launch pads are empty, the planetary encounters are history, and the radios will soon fall silent. But out there, in the unfathomable depths of the cosmic ocean, the Voyagers sail on. And they always will.